So we had a little glitch. OBS got disconnected. Can you please confirm that you can hear me and see this stuff? All right, great. So I get sometimes this things, and yeah, I'll if it goes down, just wait. I'll do my best to get back up. So for now, what we've got on the menu today is like one of those gourmet restaurants. So today we have FIFO communication. Then we have implement well popen. This is a small thing. Then we have the behind the scenes implementation of pipes, the pipes that you use on the command line. What's behind them, and that will be with DAP and DAP2. Then we will move to shared memory, and with this we're closing the processes section of this course. And then we'll talk about tests, exams, and consulting hours because we need to handle those as well. All right, so let's get started. A little review first. We worked with pipes. Last week, we needed to actually communicate between processes to transfer data from one process to another, basically to aggregate calculation results. And for that, we just used pipes, which were quite easy to use. When you create them, they get opened and they are inherited by a child process. But you cannot really use them to communicate between programs that are not related. You always have to have somebody above that created the pipe. Otherwise, there is no way to pass it around because it has no ID. All you get is two descriptors, one for reading, one for writing. So you can't really say, I would like to write in that pipe. You need to have the descriptor, and you can only have it if you inherit it. So that's where FIFOs come in and solve this issue. But before we go to FIFO, I just want to go a little bit over the special behaviors of read and write, which are identical for FIFO as they are for pipe. Although FIFO will also bring a special behavior for open. So, first special behavior. Read and write in pipes and FIFOs are actually different than for files. Read does not consult the data. Read actually removes the data from a pipe. In a file, read consults the data. The data is left there. But in a pipe, read actually removes it. Write adds data to a pipe. In a file, write could actually overwrite existing data, but also append. Well, in this case, write only appends data to the pipe. So this is the first special behavior. Second one is it's actually something about waiting and synchronizing. And you'll see this is actually quite good, but as you first bump into it, it may feel like too much trouble. So the story goes like this. Both read and write, if they are reading from an empty pipe or trying to write to a full pipe, they will wait until what they need becomes available or until there is nobody who can create that. In other words, read will wait for some data to read or until there are no more writers that could create data. Write will wait for space or until there are no more readers that would remove data and thus create space. Okay, so this is a special behavior, this waiting. And finally, neither read nor write will actually guarantee in any way that they will operate on as many bytes as you ask. You may say read 1,000, but read will only return what it gets. Same for write. You may say write 1,000, but it will only write as much as it can. If there is no more space, it will just not write. And this is normal even for a file. If you want to read 1,000 bytes from a file, it only has 15, it will read 15 and tell you, I read 15. But from a pipe, you actually need to think a little because maybe you want to read 15, but sorry, you want to read 1,000 and you only get 15, but maybe the remaining 985 are still being written. So maybe you will want to try again. So this is something that you have to implement yourself, how to insist in reading as much as you want, but read and write will not do anything about that. They will handle whatever is possible and then tell you how much they did. So handling this kind of insisting, stubborn, let's say, read and write, you can find them down here in the seminar part. You'll find an implementation somewhere, I think here. All right, if you're curious, you can look into that. Those of you who don't do a seminar with me. All right, now let's move to FIFOs. So, FIFOs can be used to communicate between any two processes. No restrictions on inheritance, but for this to happen, each process has to be able to refer somehow to the FIFO. It has to be able to identify it and say something like, I want to connect to that FIFO. With pipes, you cannot say that. But FIFOs are actually files on disk. And being files on disk, it means they have a path, which is a unique identifier in the whole system. So you practically open a FIFO like any other file. And then you write and read. So let's see what are differences. What are the differences between FIFOs and pipes? So FIFOs are files on disk, which implicitly gives them a unique ID that you can use to refer them. Now, pipe creation also opens them, but FIFOs have separate things. You create them and then you open them explicitly. There is no automatic opening of any kind. Pipes are cleaned up, are actually maybe, let's just say, destroyed. When all their ends are closed, you never really delete a pipe, you never really destroy a pipe, you just close its ends and the system takes care of the rest. When nobody else is connected to it, it frees it. For FIFOs, this is not happening. FIFO is a file on disk. If you want to delete it, you have to delete it explicitly. Also, FIFOs may live beyond the processes. Pipes don't really. When all the processes using a pipe stop, the pipe is gone. Not for FIFO though. Being a file on disk, if the process is stopped, that's their business, but FIFO is still on disk and may actually carry data from one execution to another if you are not clean with how you use it. So this may actually get you into trouble if you start your program and expect the FIFO to be empty, but actually it's not, and then everything goes down. So watch for this. All right, how do you create FIFOs? Easy. On the command line like this, or you can do it from C like this. Basically, this does the same thing as this. And here you have to specify the permissions for your FIFO. In this case, the owner has read and write and nobody else has any other permissions. And this is what I advise the students to use, because if they work on the same machine with others, you don't want anybody to be reading from your FIFO by mistake and then mess up your data. So how do you remove them? You simply delete them. Or from C, you unlink them. So let's have these two programs. You've seen this for pipes, I think, last week. It's a children's round count, eeny, meeny, miny, mo. So the first program sends to the second a number, the second sends it back decremented, then the first gets it and sends it back decremented, and so on until it reaches 0. So you've seen this with pipes. You have it somewhere higher up in the class notes. So let's see it with FIFOs. Maybe if I make this wider. Yeah, now you can see them both. So let's implement this. So first things, we need to create the pipes. We have two FIFOs, right? Sorry, bidirectional communication is what we need. So we will use one FIFO per direction, just to make sure that we are not, getting into trouble for no reason. So let's create the two FIFOs. Programs A, B. So we'll have two FIFOs. A to B and B to A, right? So now if I list, you can see that they have this P marking their type as pipe, so these are not regular files. And ls for me is configured to show me a special character that tells me a little bit about the file. So it shows me this pipe next to their name, knowing that basically it's telling me it's a FIFO. All right, so we have them. So the programs now, let's have FA. I'm going to put an F because we'll have several AB programs today. This is program A. Okay. And I think I'll need to include a few things. I don't know exactly which ones, but I'll compile and see what happens. All right, loads of them. Sorry, that was not supposed to be written there, but rather here. Okay, this I need. Let's see if anything else is required. Yeah. UniSTD. Okay. All right, we're good. So this is FA. Now I'm gonna write this into FB.C. I'm gonna delete the code, but keep the includes and just bring this thing instead. All right, so this is B. And compile. All right, so now we'll need to run them both. So we'll say FA and then FB, and here you go, right? So A sent a 20, B got it, decremented, and sent a 19. A got the 19, decremented, sent 18. B got the 18, decremented, 7, and so on until this number reaches 0, at which point the execution stops. So let's see the code and discuss the important points of it. All right, so this is the code side by side. Now, if you check the note, the lecture notes, you'll note that this piece is almost identical. What you will not see is a bunch of closing statements, but we don't need them here because we don't have pipes which are automatically open both ways. So we don't need to close things that we don't need because we never open them. So what do? We simply open the FIFO just like we would any other file. And then read and write from it and then close it. It's that easy. But there is a catch. So first of all, you open a FIFO either for writing or for reading. Don't go for read-write because it becomes weird. And second, there is a special behavior of open when working with FIFOs. And you can read it here, but I will tell you this behavior directly on code. What oh boy, what open will do when you open a FIFO is to wait until the FIFO is open for the complementary operation. So if you open a FIFO for reading, open will be stuck there until somebody opens the FIFO for writing, and vice versa. All right? Why would it do that? Well, one thing would be that when you pass open, when you pass that instruction, you know you have somebody to talk to. So that's actually a good thing. Otherwise, you'd have to keep checking, is anybody hearing you? This way, you know for a fact. If you pass open, then somebody is reading what you're writing. The problem with this is that if you mess up the order of the opening statements, programs will lock. So let me show you this first. Again, when you run FA, FA does nothing. Exactly, Radesh. If you flip, and I will demonstrate it in a minute. If you flip in one of the programs the open statements, things will get stuck. But look at this. FA is actually stuck as it is because it's opening a FIFO and it will not move on until somebody else opens it. As soon as I start FB, FB opens the same FIFO for the opposite operation, and then they both move on. So let's look at the code now that we know this thing. So when this thing starts up, this opens the FIFO and then waits. If this guy starts first, then this opens the FIFO and waits. Until when? Until it is open for the complementary operation. So this opens for writing, and when this guy is opening it for reading, they both move on to the next instruction. And this guy opens the other pipe for writing, and this guy opens the other pipe for reading, and then they both move on to the code. Now, if I come here and just do this, the programs will never move. Because this guy will open A to B for writing, and then wait for somebody to open A to B for reading. But when you start this, instead of opening A to B for reading, it will open B to A for writing and wait to be open for reading. But it will be only open for reading here. But this guy never gets here because it waits for this to be open for reading, but it's only done here, but it doesn't get here because this is waiting for this, and it doesn't get here because this is waiting for this, and you're starting to get the idea that it's a circle. Each is waiting for the other, and they're not moving on. So we can show this really easily. Let's compile FB again. And FA will stay stuck until we start FB, but this time nothing happens because they both wait for each other. So we got to close them and fix. All right. So do we have questions here, please, on this thing? Basically, the lesson that you can start getting from here, and I will keep repeating this the whole semester because it's the one important thing that you need to remember. You will bump into these situations. Yes, you have to open them into the right order, and I'm not sure you realize how right you are when you say the right order. So let me emphasize that. You will bump into this kind of locked situations. They are called deadlocks. Basically, programs waiting for a process is waiting for another one to do something, and that one is waiting for this one to do something, and they never move on from there, right? And sometimes it's not just two, it can be several. And the very simple solution to that is to always access resources in the same order. So when I'm saying, when Berzent said the right order, it doesn't really matter what order that is, but keep it the same all the time. So here, if you check, and don't worry, I'll repeat this a lot in the upcoming weeks. Here, if you check, we have A to B, B to A, A to B, B to A. If we flipped this two before, the order would not be the same. If we flip both of them, the order would be the same, but it would be a different order. It would still work as long as you keep the same order. So watch out for FIFOs. If you end up being stuck, it's probably something about this order. Okay, let's see what else we have. Yes, A to B and B to A are the names of the files. You can see them in the notes. I mentioned how you create them, and you have them here, A to B and B to A. I created them a little bit ahead of time. It's the permissions. The second parameter is the permissions. Thank you. Right? It's this stuff. All right. So that's about it for FIFO. I don't really have more than that to say. So I'm going to move to popen, unless you guys have questions. Should you have questions, just write them, I'll stop and answer. So here is popen. No, closing them in a different order shouldn't have any issue. Unless, I don't know, it would have to be a very special situations. Maybe if in between the closings you do something else, you'll have to judge. I usually open and close them like parentheses, right? Just to be on the safe side, but I've never got into trouble due to closing, mostly due to opening, or always due to opening. All right, Poppen. So this is a very simple API, Poppen, which allows you to run a program, actually to run you a shell command, any shell command, and either get back its results in the C program, or it lets you to send input to that command. So this is actually, you've probably run programs using an instruction called system in Python or in other places, right? System just runs it. popen runs it and also lets you play with the input output. But you can implement them both using exec and a few tricks that we'll just be learning in a few minutes. So let's just have a look at this API. So you all know the 99 Bottles of Beer on the Wall song. It's a really long song, right? And we write a bit of code that generates it. But we would like this to be displayed in a pager. We could obviously use a pipe in bash to show it in a pager, but I would like my C program to open the pager automatically. So here is what I do. I call popen on less, so less is the command to be executed. And I'm telling it, I will want to write to this program. So practically, I'm giving it its standard input. And I'm getting back a file pointer. And then I'm going to write to that file pointer the song. Then I'm going to close it. Watch out. It's pclose. It's not close. It's a special close. All right? And what will happen is popen will start less, and it will plug in whatever I write to its standard input, and less will display it. So if you want to see this happening, let's write a program called 99. I believe popen only needs stdio, so the includes will be rather easy here. Okay, this is it. Compile. All good. And now that we run it, you'll see that it opens it in less. You see, I can navigate up and down. All right. So this is one way of doing it. The other way of doing it is if I want to get the output of the command and then process it in C. So for instance, somebody asks you, write a C program that gets the user with the most processes. Now you can do this using the C API, or you know there is a command and you can run the command and get its output into the program. So this is what we're going to do. So we're going to have n will be the number of processes. U will be the name of the user. Hopefully it is not going to be longer than 64. This is not necessarily wise, but it's good enough. And then we simply run this command in popen. This is a shell command. And we're telling it, I want to read the output. So when this is done, I simply scanf the number of processes and the username, I close FP, and then I print out. So I'll let you execute this and see how it works. But this is pretty much all there is about Pompon.